You ask ChatGPT to cite a Harvard study on coffee and diabetes. It gives you an author, a journal, a publication year, and a DOI. You paste that DOI into your browser. The page does not exist. The study was never published. The author may not even be a real person. ChatGPT just made all of it up, and it delivered every detail with complete, unshakable confidence. No caveat, no uncertainty flag. Just a fabricated academic citation that looked exactly like the real thing. This is called a hallucination, and it is not a bug that is about to be patched. It is a fundamental property of how large language models work. To fix it cleanly, you would need to redesign core parts of the architecture. In this video, we are going to go deep on exactly why it happens, the training data, the weights, the inference loop, the incentive structure, and what the field is actually doing about it in production today. The term hallucination is borrowed from psychology, where it describes a perception with no external stimulus. In AI, it refers to any output a model generates that is factually wrong, unverifiable, or invented, but presented as if it were true. This covers fabricated citations, wrong historical dates, incorrect statistics, invented quotes attributed to real people, and multi-step calculations that look right but arrive at the wrong number. Estimates from independent evaluations suggest that between 15 and 20% of AI-generated responses contain some form of hallucination, depending heavily on the domain and the type of task. That number is higher for niche topics, recent events, highly specialized scientific fields, and anything requiring precise numerical reasoning. To understand why this happens at the architectural level, you first need to understand what a large language model actually is, because it is not a search engine and it is not a database, and conflating it with either of those things will give you the wrong mental model for everything that follows. A language model is a next token predictor. During training, it reads an enormous corpus of text, hundreds of billions of tokens scraped from the web, books, code, Wikipedia, and scientific papers. From that corpus, it learns a single objective. Given a sequence of tokens, which token is statistically most likely to come next? That learned relationship gets compressed into the model's weight with billions of floating point numbers arranged in transformer layers that encode patterns across the entire training distribution. At inference time, when you send a message, the model does not look anything up. It runs a forward pass through its neural network, samples a token from a probability distribution over its entire vocabulary, appends that token to the context, and repeats until it samples a special end-of-sequence token. Every single word you read in a response is the output of this probabilistic autoregressive sampling process. The model is not retrieving a stored fact from a database. It is generating the statistically most plausible continuation of the input sequence it received. Plausible is the key word here. Plausible and true are categorically not the same thing. Root cause 1 is the training data itself. Every model has a knowledge cutoff, a fixed date after which it has seen no text at all. Events, discoveries, court decisions, and publications after that cutoff simply do not exist in the model's world. When you ask about something post-cutoff, the model does not say, "I have no data on that." It generates the most statistically plausible sounding answer based on everything it does know about adjacent topics, which may produce output that sounds authoritative and is completely wrong. Beyond the cutoff problem, the training corpus is deeply noisy. The internet contains factual errors, satire presented as straight news, opinions confidently stated as facts, and outdated information that was never updated after the original publication. The model learns statistical patterns across all of this equally. If 70% of sources in the training data confidently assert something that is incorrect, the model learns to confidently assert it too. Rare correct facts can be statistically drowned out by the sheer weight of common misinformation in the corpus. Coverage is also highly uneven. Western English language content dominates most training sets. For niche domains, non-English topics, or highly specialized subfields, the model has thin signal and fills in the gaps with statistical extrapolation from what it does know. Root cause 2 is architectural. A language model does not store facts as discrete records the way a database does. A relational database stores the capital of France as an explicit row, a direct key-to-value mapping. When you query it, it retrieves the exact record. If the record does not exist, it returns null. It cannot invent a plausible answer. A language model stores information implicitly distributed across hundreds of billions of parameters. There is no discrete row for capital of France. There is a vast entangled statistical pattern that, when activated by the right input sequence, tends to produce the token Paris with high probability. That pattern is not localized to any single neuron or weight. It is diffused across millions of attention heads and feed-forward layers. When you ask about something the model only partially learned during training, something at the edge of its training distribution, that pattern activates partially. The output becomes a plausible approximation of what a correct answer would look like. That plausible approximation is the hallucination. There is also no mechanism to update a single fact in isolation. You cannot change one row. Update what a model knows requires retraining the entire model on new data. a process that costs millions of dollars and weeks of compute time for a frontier system. Root cause 3 is the confidence problem, and this one comes from the fine-tuning stage rather than pre-training. Language models are fine-tuned using reinforcement learning from human feedback, RLHF. Human raters evaluate model responses and score them. The model is then updated via reinforcement learning to produce responses that score higher. The core issue is that confident, fluent, helpful-sounding answers consistently score higher than hedged or uncertain ones. Saying, "I believe this might be the case, though I am not certain," scores worse than asserting the same content as a direct statement of fact. Training pressure systematically rewards confidence. Over hundreds of thousands of gradient steps, the model learns a strong prior toward sounding certain, regardless of whether the underlying token probabilities actually justify that certainty. There is also no internal truth verification step that runs before tokens are emitted. The model's attention mechanism weighs contextual relevance, which parts of the input are most useful for predicting the next token, not factual accuracy. The model has no internal signal that distinguishes "I know this" from strong, consistent training data from "I am pattern matching to something adjacent and generating a plausible extrapolation." It has no pause and check mode, it simply generates one token at a time. Hallucinations break into three recognizable failure modes. Fabrication, sometimes called ex nihilo hallucination, is the most visible. The model generates content from nothing. A paper that was never written, a law that was never passed, a company that does not exist. These are triggered when the model receives a query with zero or near zero training signal and responds with a statistically plausible sounding substitute. Contradiction is subtler. The model states something in one section and contradicts it later in the same response. Transformers have no persistent working memory. Each forward pass processes only the tokens in its context window. There is no global consistency checker ensuring statement 17 is compatible with statement 3. Long responses and multi-turn conversations are especially vulnerable to this. Conflation is when the model merges properties of two distinct but similar entities. It attributes the discovery of one scientist to another in the same field because both names appear near the same words throughout the training corpus. It blends details of two cities with similar names. The root cause is that their statistical representations in weight space are close together, so the model generates a blend rather than either correct answer individually. What is the field doing about this? Several mitigations are in production and some are highly effective. Retrieval augmented generation (RAG) is the highest impact intervention available today. Rather than relying on parametric memory, a RAG system retrieves relevant documents from a verified external knowledge base at query time, injects those documents into the model's context, and requires the model to ground every factual claim in a retrieved source. This shifts the bottleneck from "does the model know this" to "did the retrieval system return the right document?" A tractable engineering problem with well-understood solutions. Well-implemented RAG reduces hallucination rates dramatically on factual tasks. Tool use and function calling push this further. By giving the model structured access to calculators, code interpreters, live search, and databases, you substitute direct computation for unreliable parametric recall. The model does not need to remember a specific statistic if it can call an API that returns the exact figure. Chain of thought prompting requires the model to reason through a problem step by step before committing to an answer. The intermediate steps make logical errors visible before they get embedded into a final conclusion. It reduces hallucination on multi-step reasoning tasks without any changes to the underlying model weights. Grounding and citation requirements force the model to attribute every factual claim to a specific source. This does not prevent fabrication, but it makes fabrication detectable and auditable. If a model must cite where every claim came from, a fabricated source becomes immediately apparent upon checking. None of these fully solve the problem. Calibration, getting a model to accurately represent its own epistemic uncertainty in real time, remains an open research problem at every major AI lab. The model does not know what it does not know, and until that changes fundamentally, hallucination is not a bug you can file a ticket on. It is a property of the architecture. Knowing that is what lets you use these systems well. RAG and tool use for anything where factual accuracy matters. Citation requirements that make fabrication detectable and checkable. Appropriate skepticism in thin signal domains. The models are extraordinarily capable. They are not a ground truth and they were never designed to be. If you found this useful, like and subscribe. See you in the next one.